In this video, we're going to talk about mass relationships in chemical reactions and how the ratios of moles between different elements, compounds, or molecules in a chemical reaction provide a lot of data about the reactants and the products, the relationship between the two, and how if you know one value, you can obtain a lot of the other values in the balanced chemical equation. So first, let's start out with a balanced chemical equation. Here we're going to use as an example the combustion of butane, which is C4H10, and we know that combustion requires oxygen, gas in the form of O2, and combustion produces CO2 and water, H2O. And so what we immediately notice is that this is an unbalanced chemical equation. And so of course, if we want to balance this equation, we need coefficients. And the coefficients are 2 for butane, 13 for oxygen, 8 for carbon dioxide, and 10 for H2O. And so now that this equation is balanced, it tells us much more about what is being consumed and what is being produced quantitatively. That is the number. And it also talks about the ratio. So if we were to have 2 moles of C4H10 in the presence of excess oxygen, or at least 13 moles of oxygen, we would produce 8 moles of CO2 and 10 moles of H2O. Now that we have coefficients, we know a lot about the relative number of moles being produced and consumed in this combustion reaction. And these coefficients can represent one of two things. These coefficients can represent molecules. That could be 2 butane molecules and 13 oxygen molecules. Or, like I was saying earlier, they could represent moles of a substance. So this could be producing 8 moles of CO2 or 8 molecules of CO2, 10 moles of water or 10 molecules of water. The beauty of the balanced chemical equation is that these coefficients represent ratios that are consistent whether we're talking about molecules or moles, because we can't produce more than 8 moles of carbon dioxide and 10 moles of water from 2 moles of butane. We can't do it. If we have 2 moles of butane, the most CO2 we can produce is 8 moles of CO2. Same with molecules. If we have 2 molecules of C4H10, we cannot produce any more than 8 molecules of CO2. Balanced chemical equation communicates this quantification and these mass relationships between the reactants and the products. And with a little conversion, we could also have grams. By multiplying moles by the molar mass of any one of these reactants or products, we can get their mass in grams. So for example, butane, we have 2 moles of C4H10. We can multiply that by the molar mass, which we know the molar mass is in grams per mole for C4H10. So 1 mole of C4H10 weighs or has a mass of 58.12 grams. And we cancel out our moles of butane so that we get grams of butane, and that gives us 116.2 grams of C4H10. So 2 moles of butane is 116.2 grams. And we can do that for all the rest of them. 13 moles of oxygen is 416 grams, 8 moles of CO2 is 352.1 grams, and 10 moles of water is 180.2 grams. So every combustion reaction of butane that occurs in the world at any time follows the molar ratios outlined in this balanced equation using those coefficients. So let's look a little bit more about the molar relationships here. So let's look, for example, at the molar relationship between butane to oxygen. So for every 2 moles of butane, C4H10, we have a ratio of 2 moles butane to 13 moles of oxygen. And a ratio is the same thing as a fraction. So we can say we have 13 moles of oxygen over 2 moles of butane. Or equivalently, we could say that we have 2 moles of C4H10 to 13 moles of oxygen. And these two ratios would be used depending on what you're trying to accomplish. If you're trying to eliminate moles of oxygen and obtain moles of C4H10, you would use this, because then you can cancel moles of oxygen in the denominator. Likewise, if you were trying to eliminate moles of butane and get moles of oxygen, you would use this first ratio, or fraction, or relationship, to eliminate moles of butane in the denominator. And you can create one of these ratios, or molar relationships, with any of these reactants or products in the balanced chemical equation. But you need the balanced chemical equation in order to do that, because then you know the relationship between one reactant and one product, or one reactant and another reactant, or one product and another product. So in that way, we can make a relationship between butane and carbon dioxide, or oxygen and water and butane, or any combination, because we have the molar relationship through the coefficients in the balanced chemical equation. So here's a question. Let's say we have 6.16 moles of butane, C4H10. How do we know how many moles of oxygen are needed to completely consume all of that butane, to completely combust that butane? Well, we use a fraction to convert the number of moles of C4H10. So we multiply by a fraction. And so what are we trying to get? We're trying to get moles of oxygen. So that will be in our numerator. And our denominator will have moles of C4H10, so that those units will cancel out, leaving us with moles of oxygen. And like we said earlier, moles of oxygen to moles of butane is 13 to 2. We have that relationship right here. So 13 moles of oxygen for every 2 moles of butane. That gives us 40.0 moles of oxygen. Now let's say we want to know how many, let's say we still have 6.16 moles of butane, but we want to know how many moles of CO2 are produced from that many moles of butane. So we have 6.16 moles C4H10. We're going to multiply by a fraction, a molar relationship. We still have moles of C4H10 in the denominator because that cancels here. And we want to get moles of CO2 produced. We know that 8 moles of CO2 are produced for 2 moles of butane reacted. That gives us 24.6 moles of CO2. And just to show you, you don't need to start with moles of butane. We could start with this number of moles of oxygen, so we can do 40.0 moles of oxygen. And we can multiply that by a molar ratio to get the same number of moles of CO2. So if we multiply that by moles of O2 in the denominator and moles of CO2 in the numerator, we know that 13 is the coefficient for O2 and 8 is the coefficient for CO2. we see that 40 times 8 divided by 13 is still 24.6 moles of CO2. So notice, we get 24.6 moles of CO2 if we start with either the number of moles of butane or the number of moles of oxygen. And it's because we have the coefficients in our balanced chemical equation, and those coefficients are the molar relationships between these compounds that enable us to calculate the amount of products produced from a given number of moles of butane or oxygen, or we could back calculate the amount of reactants if we're given a number of moles of product produced. So for example, we can go from this 24.6 moles of CO2, we could go back and see how many moles of oxygen were consumed or how many moles of butane were consumed by using these fractions, these molar relationships, in our calculation. And so let's look a little bit about the relationship between these different units. We have mass and moles and molecules, number of molecules, that is. And we can convert from one to the other quite easily. We know that mass is measured in grams, and moles are, of course, moles, and the number of molecules is measured in a number. And so what's our conversion factor between mass and moles? Well, that's going to be something that involves both grams and moles, because if we go from moles to mass, we want something that will give us grams, but eliminate moles. So that would be grams over moles. But what that conversion factor is the molar mass, because that is in grams per mole, or if we get the inverse, that's just moles over grams. And in this way, we can eliminate moles or grams, convert from mass to moles, or moles to mass. Now going from moles to number of molecules, we of course use Avogadro's number, which is Na and 6.022 times 10 to the 23rd. And what is that? That's the number of molecules, or atoms, number of molecules or atoms, in 1 mole of a substance. So if we want to go from moles to molecules, we multiply by Avogadro's number, and we eliminate moles in the denominator. If we want to go from number of molecules to moles, we divide by Avogadro's number, which is the same as multiplying them by this inverse, 1 mole over 6.022 times 10 to the 23rd molecules. In this way, we would obtain moles, cancel out molecules, and get the number of moles of a substance. Let's say we wanted to go from moles of A and convert to moles of B, or the other way around. In order to do that, we need the coefficients from the balanced chemical equation. So let's say we have 2 moles of A. In order to get moles of B, we need to multiply by a fraction with moles of A in the denominator to eliminate moles of A, and moles of B in the numerator, so that's what we get in the end. Let's say we have a relationship of 3 moles of B to 2 moles of A. Well, we know that moles of A will disappear, and 2 times 3 divided by 2 gives us 3 moles of B. So we can use the coefficients to convert from number of moles of any of our reactants to any other reactant or to products. That's the beauty of the mass relationships, or the molar relationships in chemical reactions.